The question of which programming language reigns supreme for hacking is not one with a simple answer, as the digital landscape of cybersecurity is too vast and varied for a single tool to dominate all its territories. Instead, the best language is entirely contextual, dependent on the target environment, the phase of the attack or assessment, and the specific objectives of the security professional, creating a toolkit where Python often serves as the versatile multi-tool. C and C++ provide the low-level surgical instruments. JavaScript and SQL act as specialized keys for specific digital locks, and languages like PowerShell and Bash form the essential automation glue that binds complex operations together. For the broadest range of offensive security tasks, from rapid prototyping of exploits to automating reconnaissance and building sophisticated security tools, Python has firmly established itself as the de facto lingua franca of the ethical hacking community, prized for its clear, readable syntax, extensive standard library, and a vast ecosystem of security-focused packages that make it exceptionally efficient for tasks ranging from writing socket-based network scanners and crafting custom HTTP requests for web application testing to parsing and manipulating binary data for forensic analysis or fuzzing. The power of Python lies in its unparalleled flexibility, with libraries like Scapy for packet manipulation, requests for elegant HTTP interactions, PyCrypto for implementing cryptographic attacks, PWN tools for exploit development, and Beautiful Soup for web scraping. A security researcher can quickly translate a novel attack concept into a working proof of concept with minimal boilerplate code, making it the ideal language for the initial exploration and weaponization phases of a penetration test, where speed and adaptability are paramount. Furthermore, its seamless integration with C libraries through bindings means performance-critical sections of a tool can be optimized without sacrificing Python's rapid development cycle, while its prevalence on Linux systems, the primary operating system for most security professionals, ensures it is almost always available for use in the field. However, to truly understand and exploit the fundamental vulnerabilities that exist at the heart of modern software, particularly those involving memory corruption, one must descend from Python's high-level abstractions into the raw, unforgiving realm of C and C++. These languages provide the granular control over memory management, or more accurately, the mismanagement thereof, that is necessary to comprehend and weaponize classic vulnerabilities like buffer overflows, use after free errors, and integer overflows that plague applications written in these same languages. When analyzing a vulnerable C-based service, understanding how the stack is structured, how the heap allocator functions, and how CPU registers are manipulated during execution is not academic. It is the practical knowledge required to craft a working exploit that hijacks control flow. Debuggers like GDB with enhancement plugins like PEDA, and disassemblers like Ghidra and IDA Pro operate at this level, requiring the hacker to think in terms of pointers, memory addresses, and assembly instructions. Writing shell code, the compact position-independent assembly payload that gives an attacker control, often begins with writing it in C before compiling and extracting the raw opcodes. For reverse engineering proprietary software, developing kernel-level rootkits, or exploiting firmware on embedded devices, a deep proficiency in C is not merely beneficial, it is indispensable. It is the language that speaks most directly to the machine, and to defeat an enemy that operates at that level, one must be fluent in its native tongue. In the domain of web application hacking, which constitutes a massive portion of modern attack surfaces, a completely different set of languages becomes critical. Here, JavaScript is unavoidable, both on the client side and increasingly on the server side with Node.js. Understanding JavaScript is essential for discovering and exploiting cross-site scripting, XSS vulnerabilities, manipulating the document object model, DOM, bypassing client-side security controls, and attacking Node.js application logic. Similarly, SQL, structured query language, is non-negotiable for identifying and exploiting SQL injection vulnerabilities, one of the most dangerous and prevalent web application flaws. A hacker must understand not just how to inject a malicious quote to break a query, but how to leverage union-based, error-based, blind, and out-of-band techniques to extract data, bypass authentication, and even achieve remote code execution, often requiring knowledge of dialect-specific nuances in MySQL, PostgreSQL, Microsoft SQL Server, and Oracle. For testing modern web applications, familiarity with PHP remains valuable due to its historical prevalence in legacy web systems, where understanding its quirky type, juggling, and outdated functions can reveal critical vulnerabilities, while knowledge of Java is crucial for penetrating large-scale enterprise applications that often run on Java-based frameworks like Spring and Struts. On the Windows operating system, which dominates the corporate environment, PowerShell has emerged as an incredibly powerful tool for post-exploitation and lateral movement. Its deep integration with the Windows ecosystem allows an attacker with initial access to perform reconnaissance, escalate privileges, dump credentials, and move laterally across a network with a level of stealth and efficiency that is difficult to achieve with other tools. The ability to write and execute PowerShell scripts entirely in memory without touching the disk makes it a favorite for advanced persistent threats, APTs, and red teams alike. On Unix-like systems, including Linux and Mac OS, Bash scripting fulfills a similar role for automation, allowing hackers to chain together command-line utilities to create powerful reconnaissance scripts, automate brute force attacks, and manage payloads. Beyond these core languages, specialized scenarios demand their own tools. Assembly language is the final layer of abstraction, necessary for crafting custom shellcode, analyzing packed malware, and writing exploits for architectures beyond the common x86-64, such as in IoT hacking. For mobile application security, knowledge of Java and Kotlin for Android, and Swift and Objective-C for iOS is required to reverse engineer apps, analyze their binaries, and understand the security models of the respective platforms. The burgeoning field of blockchain and smart contract security has created demand for knowledge of Solidity, the primary language for Ethereum smart contracts, where understanding its peculiarities is key to finding reentrancy, integer overflow, and logic flaws that can lead to the loss of millions of dollars in cryptocurrency. Therefore, the pursuit of the best hacking language is a misdirection. The truly proficient hacker is not a monolingual programmer, but a polyglot who possesses a working knowledge of this entire spectrum. They understand that a sophisticated attack might begin with a Python script for network reconnaissance, leverage a custom C program to exploit a buffer overflow in a service, use SQL injection to pillage a back-end database, and then employ PowerShell to establish a persistent foothold in the Windows domain. The best language is the one that most effectively solves the problem directly in front of you. And the master hacker's skill lies not in memorizing syntax, but in cultivating a deep understanding of how computers work at multiple levels and selecting the appropriate tool to manipulate that reality to achieve their objective, whether that objective is to strengthen defenses or, in the case of the ethical hacker, operating with permission to prove their fragility before a malicious actor can do the same.